everyone. Welcome back to part two of generating zkMIPS proofs with ZKM. Be sure to check out part one if you haven't already. In this part, we'll be going through the demo portion. So we'll be going to write a program proving that a user knows the value of a corresponding SHA-256 hash using ZKM's Prover Network. The Rust and Golang versions for these programs are part of ZKM's project template that you can use. We'll then generate a proof using the Prover Network for this example, but you could also use your local machine if you'd like. And if that proof is valid, we'll deploy a verifier contract to verify that proof. And then if that proof is valid, we'll be able to mint an ERC20 token. That's our on-chain action that we're doing here. So as an overview of how the general flow looks using the project template, which you can find right here with this link, we can first build our guest program, either in Rust or Go, which are the languages that ZKM is compatible with right now. And the project template includes host programs that we can reuse after we generate the ELF of the guest program. And then from here, we can either choose proving on our local machine or using ZKM's Prover Network to generate that proof, depending on your preferences and if you have the hardware requirements to do so locally. From there, we can generate the verifier contract. And this project template provides a very streamlined process for completing all of the steps in this flow. And that process encodes these three main stages that we saw previously in part one of this two-part series. So that includes our program execution, the proof generation, and the proof verification. Now, going into some more details for the first stage of the program execution, our first step is writing the programs. So for our ZKVM, we have both a guest program and a host program. The guest program will execute the ELF binary that is proven inside of the ZKVM. So its main functions include reading the inputs that's provided by that host, writing private outputs to that host, and then also committing any public outputs to the journal. The host program, on the other hand, will set up the environment for that guest program and evaluates those results from the guest execution. So its main functions here, instead of reading the inputs, it supplies the inputs to the guest program. It'll evaluate the private outputs provided by the guest, and then it'll also evaluate the public journal output that is also provided by the guest. So those are the main interactions that we see between the guest and host programs. Taking a look at some practical examples for guest and host programs. For this particular example of proving that a user knows the value of a corresponding SHA-256 hash, we can see that. So for example, over here, these lines, we're getting the user inputs. Next section here, we're evaluating the result of the computation for our program that it's performing before we commit the public outputs and result for the proof. And on the right side here, this is the equivalent guest program written in Golang. And then here we have our equivalent host programs. So we're splitting in our first section here, we're splitting our ELF into segments, and then we're loading our inputs, evaluating the private inputs and also the public journal outputs from the guest. And then here is our Golang equivalent as well. So these are the programs that we'll be using for today's example, specifically the Golang version. Now, in the second stage for proof generation, once we have our programs written, we'll first discuss in more detail of the two types of proving that's offered by ZKM and also just in general. So this includes both local proving done on the client side and also remote proving done on the server side. So some differences between these. For client-side local proving, these proofs are generated locally by the user yourself on your own hardware. And some benefits of using local proving is that you can also generate proofs for privacy-based applications. Any kinds of private inputs that you put will just be kept locally. It's also decentralized, so anyone with these hardware requirements can generate proofs. Whereas for server-side proving, remote proving, like what ZKM's Prover Network offers, this involves, instead of generating your proofs locally on your own hardware, this involves outsourcing that proof generation to other servers. And it's an alternative if you want to do some especially computationally intensive tasks that you may not have the hardware for. And it can be decentralized, as in decentralizing the different prover roles that are involved in the network that you're using. And there's different types of server-side provings that you can have. So, for example, proof networks, which service single applications, and then also proof markets, which service multiple applications in an open market. So those are some of the different types of um, remote proving techniques. And then from here, we have both our local proving, which we offer, and then remote proving, which we offer through ZKM's Prover Network. Now, for ZKM's proving service specifically, our proving service allows developers, anyone who's using zkMIPS, to efficiently generate proofs, and it's an alternative to generating them locally if you don't have the hardware requirements and or want faster proof generation. And it's also more suitable for some complex programs because these proofs can be generated in parallel. And if you are interested in having a spot on our whitelist to use a proving service, you can go ahead and apply here. So for generating proofs, there are a couple of ways that you could go about proving your guest program, like what we discussed. One is locally, if you have the minimum hardware. If you don't, you can use our proving service. So those are our two ways that we offer for proving our guest program. In terms of general steps that we have here, we'll first compile that program into the MIPS ELF, split that ELF to individual segments, and then aggregate those individual segments for a final proof. And then after you aggregate for your final proof, you'll get a verifier folder with these three kinds of JSON files, and which will also include your final snark proof that you can verify. So we'll use these files for the proof verification part. Now, in our last stage, after we have our program execution and our proof generation, now we just have the proof verification. So we'll first discuss about some of the different verification types, which can be done locally or on-chain. And we'll be showing the on-chain case, which is deploying a verifier contract in our demo. But here, you can either verify your proofs locally, so you can independently verify the validity of a generated proof off-chain without having to rely on any sort of external parties. So very similar to if you were to generate your proof locally, you're just using your local hardware to do so. Or another way is to verify your proofs on-chain. So you can verify the validity of your generated proof by deploying a smart contract, and this will be on public and immutable as well. And in terms of what is needed for verification, the different components is your proof, your compiled MIPS program, any public inputs that you used, and also the verifier program. And once we have our proof generated, we can go ahead with creating the verifier contract. So basically, we can generate that verifier contract customized to the MIPS binary of the program that we are proving by using the verifying key that's created from the proof generation. And it'll determine from here if the proof is valid or invalid. And then that proof will be posted to our deployed verifier contract. And in our specific example, this will compare the hash of the inputs to the hash of the outputs. So the proof is valid if the hash of the value that the user provided is equivalent to the hash of the proof's output for our example that we're using. And from there we can perform any kinds of on-chain actions, like for example, in our case, minting tokens using the valid proof. And if the proof is invalid, we won't be able to do that on-chain action. Now, before going into the demo, I just wanted to add this section here and briefly discuss a new development based on the recent release of zkMIPS Plus, which includes proof composition and also precompiles. So for proof composition, while doing this, it acts as a standalone program which generates a verifiable proof for its program. So for example, hashing a given input, we'll demo that in a bit. And where this composition component comes in is that proofs can be reused by other programs. without having to re-execute that original computation. And this is also fully upgradable. So we can support verification of any proof type without having to modify the existing on-chain verifier. Now, going into some more detail into the flow of ZKM's proof composition process using the SHA-256 example that we've been using in terms of the exact steps of this process, there are three main programs that play different roles within this composition. So we have our precompiled program. Its main role is to generate a proof in our example that verifies the SHA-256 hash and on specified public inputs and producing the expected hash output and receipt. So that kind of precompiled proof, which we call the inner receipt, is stored as an assumption, and it's also reusable by some other programs that are involved in this process. And then we have our host guest program. So what this program does is it takes its inner receipt and verifies that the program's image ID and public input matches the referenced assumptions that are already there. And so all of these assumptions can then be added into a list. And then for our main host program, its main function is to produce a composite receipt. And it's the proof that addresses three main things. One, that the precompiled proof was successfully verified. Second, that the precompiled proof was correctly incorporated into the assumptions used list. And then third, we have a valid composite proof that aggregates all of the assumptions from that assumptions used list and the main host program's proof into a single verifiable receipt. So that single verifiable receipt is the result of that proof composition. Now for precompiles, their main role is to accelerate certain operations on the ZK VM, which allow for a lot faster proof generation. You can think of them as similar to specialized chips on the CPU, which performs operations a lot more efficiently. And it does this by reducing the program's instruction sequence. So for specifically with zkM's precompile, we can extend instructions to zkMIPS via system call. So right now, there is a SHA-2 precompile that's available. We'll also have a keycheck precompile that will be available, some other field operations. And you can call the extend instructions using zkMIPS's runtime SDK. And those can be constrained inside the ZKVM runtime itself, just like any other types of standard instructions. So for example, with the SHA-2 precompile, what this does is it implements some specific components within the SHA-2 hash function. So it includes the block decomposition and hash computation phases of the hash function, and overall, it can reduce the overall proving time and in the number of committed cells before padding. So it accelerates just the SHA-256 hash function that's being used in whichever program that you are implementing. And so these are just the main developments that we recently had at ZKM and which you can start incorporating for any other new types of programs that you were trying to prove. Now, for the walkthrough demo portion, if you'd like to follow along with this demo, I linked some of the resources that we'll be using. So what you should do is clone the project template repository as well as the use cases repository. I also linked some other helpful resources over here. So for example, the quick start example, and then any sort of guides that you may need for the generation and verification aspects. And then also the ZKM team has a playground available so you can complete all of these steps of this proof generation, proof verification lifecycle without having to install or set up anything. So I have the user guide over here. And then be sure if you are following along to have these requirements for Rust and Golang, and then also to install the Foundry toolchain because we're using these contracts for our verification demo. So here are all the resources that you will need for the walkthrough. Now for this first part of the demo, I have a pre-recording that I will make in 2x speed to save some time. The proof generation part, unfortunately, does take a lot of time, so we're not able to do it live, but you can do that part on your own. And once you've in terms of the actual steps, pull the latest version of the repositories. You can go to the ZKM project repository, and let me just speed this up a bit. So we're using the Golang version of the SHA-256 program and ZKM's Prover Network for this. But in our first step over here, we're installing the zkMIPS Rust toolchain. You can add this target to the Rust compiler in your development environment, and that allows you to do platform-independent computations of your Rust programs into binary ELF. So that can be completed on any platform that's supported by the native Rust compiler. So you can add this toolchain directly. And in this next step, we are building the guest program ELF binary for the Golang program. And once you have this complete, you should have an outputted ELF binary over here, your compiled program. And from here, as our next step, we will be compiling the Snark library and building our host program. And once this is complete, if you go under target and under a release, you should see your ELF binaries for the host program compiled here. Now, in our next step, before we go ahead and generate the Groth16 proof, we'll make some adjustments to this run proving script, which can be found under the host program folder. And that script is to facilitate the generation of proofs both locally and over the proof network. So remember, you have the choice to do either, depending on your preferences. And since we're using the proof network, we'll go ahead to first set the ZKM Prover to be network. So comment out where it says local. And then it's also important for you to specify your private key that corresponds to the address that you have whitelisted to ZKM's Prover service in order for you to use the proof network. And it should be already approved to be used for the network. And then you also have the option here to set some other kinds of parameters like your segment size. The ELF will basically be split into segments according to the set size that you put based on the number of cycles. And then you can also add any kinds of input arguments to your program here. So here we have our public inputs that we specified. And be sure to also set the environment variable, the setup flag, to true so that we can generate the proof key, the verification key, and the verifier contract. And all of that is needed for our next part with the proof verification. So then over here in our next step, we are running the script for the Go program, and we can also view the proving log, which we're completing in our next step here. And here's the start of our log, but we can see first that our segments are being split first, and then we're going through those different proving stages for that final Groth16 proof. So how long it takes for this proof to be generated depends on your local machine if you're doing it locally. But if you're using ZKM's Prover Network, depends on how many other proofs are queued in that network. So I'm going to switch over to the next part of this demo, just so we don't have to wait for this proof to be generated. But after your proof is generated, your proving log will look something like this. So first, as we can see, the first step is splitting the task or splitting the program into segments. And then here are the different proving stages. And then as a final result, after the proof is generated fully, you can view the total proving time, and then it will say the generating proof successfully. That main Snark proof will be under your contracts folder over here. So you can view your Snark proof with public inputs in this folder. So in addition to your proofs, the proving key and also the verifying key will be saved under there. That's where your final proof is also saved, and we'll be verifying that proof and using it to generate this verifier contract. So first, we will, from here, you can also view how long it took the proof to generate as well. But from here, we'll first be running some tests. And one is to test a valid proof, and another is to test if we have a valid proof with those public inputs, verifying that the snark proof was successfully generated. So as we can see, our two tests have passed here. And that specific test command will locally verify the validity of the Groth16 snark proof that we generated. And if we have an invalid proof, or if we didn't successfully generate our proof, those tests will fail. So this is how you can verify your proof locally. Now, if you want to do this on-chain, we can now deploy the contract with our verifier proof. So you can specify your parameters here. So we're using the Sepolia test network for a contract to be generated on. And then you should also specify the key that you're using. But from here, right now it's compiling and okay, waiting for it to end. From here, you'll have a success hash that's outputted if this contract was successfully deployed. We can go ahead to Sepolia, just copy that hash, go ahead to Sepolia, and then view our newly generated contract over here. So those are the steps for verifying your proof both locally and then also deploying a verifier contract with that verified proof. And so now that we've successfully generated and verified our proof, let's use a verifier for some on-chain actions. In this part, we'll be using the valid proof that we just generated and verified to mint in ERC20. So first, we'll change our directory to the use cases repository, specifically into the hardhat folder. We're using hardhat for this. And from here, we can now redeploy our contracts. Before you complete this step, there is a folder under the hardhat folder called test. So in there, be sure to replace the snark proof that you generated during your proof generation with the Groth16 proof that you just generated, specifically the one that we had after running through all the proving steps, depending on if you're using the local proof generation or through the ZKM Prover Network. And from here, this will take some time to redeploy our contracts, but fast forwarding a bit, we can see our deployed address here. And what you should do is you should go to the caller file and replace the contract address with our newly deployed one right over here. And then from now, once you have that, you can go to your wallet and import the token contract address that we just generated. So that's what we're doing in this step. And right now, since we do not have any minted tokens, it will show up as 0. But going back over here, we can now, as our next step, just fast forwarding a bit, we can now build and compile the color file and then finally mint the ERC20 token and specify the address that you're using. So just going back a bit here, after you successfully mint it, we can use the transaction hash that's outputted and taking it and viewing it on Sepolia, just fast forwarding a bit. It should say success in the status. If you, for any reason, use an invalid proof, it will either say that the proof is invalid or the execution reverted. But now going back to our wallet, we can now see that we have one ERC20 that's minted on this contract because we used a verified proof. So that concludes our demo. We were able to first generate a proof proving that a user knows the value of a corresponding SHA-256 hash. And then we deployed a verifier contract to verify that proof. And then finally, we used the valid proof to mint an ERC20 token. Now, in terms of our use cases, zkMIPS currently supports any native Rust and Golang programs, and we encourage developers to build any use cases that you may want to explore. So, for example, like what we had in our example, performing some action with valid proof, like minting an NFT or an ERC20. If you're interested in governance, identity verification, querying answers from an ML model, which goes into zkML, asset transaction verification. The number of use cases here really are endless, and we encourage you to try the ones that you're interested in out. But if you are interested in generating your own use cases, you want to quickly generate these proofs, you don't have the hardware requirements, be sure to apply for a spot on the whitelist here. I have a QR code here for your convenience. We do have a limited number of spots available, so be sure to do this as soon as possible. And as always, if you have any questions or run into any difficulties, join our Discord, tag anyone from the team, or shoot me a message, and we'll get back to you. But yeah, thank you so much, everyone, for tuning in and listening.